So this week I wanted to go through the quiet side BHP calculation. And the quiet side BHP calculation is a very powerful option in the software, but you need to make sure that the assumptions that you are um, making are valid when you apply it. And I wanted to just read out what the manual says directly when it comes to a quiet side BHP calculation. But before I do that, this schematic right here is a graphical way to explain what is actually happening. So when you do a quiet side BHP calculation, you assume that the annulus is filled with a single phase fluid that has communication to the flowing side at the end of tubing. So there needs to be no isolation packer, and that's very important. If you have a packer, well, then this method might not be for you. And then the BHP calculation itself is a combination of this, from the end of tubing to the top perforation, and then it's a static fluid column from end of tubing to the wellhead. The beautiful thing about this and why it's more accurate and less noisy is that this calculation in the annulus becomes a very simple one. It's a single phase fluid type of calculation with no multi-phase flow effects. And hence also the results will also be much less noisy. Since it's also a function of less input, the calculations themselves would be way more accurate. And typically, no matter what correlation you're picking, you would get very similar answers. The reason for that is, for instance, if you assume that your annulus is filled with single-phase gas, we know that once you're dealing with single-phase gas, then all of these correlations are essentially predicting the exact same value. So over to the manual. I just want to read this to you real quick. This is directly from the Whitson Plus manual, and it talks about the static quiet side calculation. The user may select which side of the tubing the bottom hole pressure calculation should follow. Using the static side of the tubing assumes that there is no single phase, or it assumes that there is a single phase gas column with communication to the flowing side at the end of tubing. So there's no isolation packer. The static side calculation is well suited for instance, gas lift wells where where it is certain that the static side is filled with gas at least down to the gas lift valve. The figures below, and that's figures in the manual, is very similar to the ones I showed on the last slide. They explain how the static side calculation works for a naturally flowing well and a gas lift assisted well. The flow path in this case is set to tubing, but the static side calculation also works when a flow path is set to annulus, with everything being reversed compared to the figures below. So that's back to the manual. For gas-assisted wells where the gas lift configuration is set to include the valves or automatic, it is also possible to select whether to use the static size calculation down to the gas lift valve or to the end of tubing. In Whitson Plus, if I pull up Whitson Plus here, I've made some calculations for this particular well, and those calculations I have now done with the flowing side. But if I went in here, and I'm also going to toggle on the other calcs here. So here you see, we have Basin Brill, Hagedorn Brown, Boltzmann, and Gerard. Very noisy, especially very noisy when it starts to, pretty similar in the beginning, single phases predicted in the well bore, and then multi-phase effects comes into play, and these different correlations, they start to spread. So if I wanted to go in and calculate this with the quiet side, because this is a gas lift well, so I'm going to make that assumption. I would just go in here, say, okay, this is the quiet side calculation. So I'm going to do that here. Click static side, click save, and then I'm going to go in and calculate this particular option right here. You see how much more or how much less noise it is. You also see that the calculations themselves, the different correlations, they're almost the same. And that goes back to the point, that if it's a single phase fluid, all of these correlations will give you the same result. The main difference between the correlations is how they estimate the so-called liquid hold-up correction factor.